habis chapter 2 ni. Wondering juga saya. Sebab space KL dia orang cakap dia nak buat sampai chapter 2 habis. Okay. Okay, so we continue with the generation. Macam mana kita nak hasilkan single sideband suppressed carrier. Macam mana kita nak generate, okay? Single sideband suppressed carrier. So can be raised is either two way, okay? Into step, okay? Kita generate dulu double sideband suppressed carrier. Kita generate tu dulu, kemudian kita filter. Maksudnya filter tu akan buang yang kita tak nak lah. Okay, mula-mula
Doktor,
kita
sorry
hasilkan.
doktor.
Ya.
Slide doktor tak ubah lagi.
Tahu bah? Ni?
Saya nampak desktop doktor.
Eh?
Ada cancel. Nampak doktor tengah jalan tu.
Oh, salah share screen kot. Okay. So nampak eh? Okay. So for the single sideband suppressed carrier, mula-mula cara nak hasilkan dia ada dua. Mula-mula kita hasilkan double sideband suppressed carrier. Okay, macam ni. Kita hasilkan dulu double sideband suppressed carrier. Ada dua lah. Maksudnya carrier je tak ada. So kita ada lower sideband and upper sideband. Selepas itu, step kedua ialah kita filter. Kita filter dengan menggunakan bandpass filter. Kita nak fokusi kita nak. Contoh kita nak lower sideband je. Jadi kita letaklah bandpass filter kat sini. So yang ni kena buang lah. Sebab yang kena pass lower sideband. So bila kita buat macam ni, so kita dapatlah single sideband suppressed carrier. So our bandpass filter, the range is depending on which sideband that we want to transmit. Okay. So first step, we just produce first the double sideband suppressed carrier, and after that we introduce bandpass filter. So bandpass filter is a tuned circuit that is very selective, that we choose either LSP or USB lah. Yang ni apa yang saya cakap tadi. Okay. Not important sebenarnya which sideband will be selected because both sideband ada duplicated same information. Yang ni single sideband generation, another method. Okay. Just now is the direct method. Direct method memang easy biasanya. Just macam ni. Indirect method, sama lah macam tadi. For double sideband suppressed carrier, indirect method panjang. Okay. The same for same goes for single sideband suppressed carrier. Panjang lah indirect method. Okay. So indirect method, another method is using two balance modulator. Okay, two balance modulator. Then we produce double sideband suppressed carrier with 100% phase difference. Okay, the circuit is called a phase shifting circuit. The entire circuit is called a phase shifting circuit. Okay, so you nampak sini, this one is your original VM. Okay, here going to balance modulator. Okay, 1, and it will produce EM cos omega M cos omega C. Okay, by having mixed with omega C. Okay, you have this as V1. And parallelly, the same EM will be going through a 90-degree phase shift because cos and sine related by shifting of 90 degree. When we shift by 90 degree, you will have instead sin function. Okay, and after that, it will go to the modulator to be modulated. Okay, we have cos omega C here. Okay, being used directly for the top process. However, for the bottom process, we're going to shift it first by 90 degree. Similar concept, because it's cos, we introduce 90 degree phase shift, it's going to produce sin function. Okay, so sin times sin. So that's why you have sin function here. Okay, and then you will mix them together with having both of them as plus. Okay, so you're going to have this function V1 plus V2 lah. Okay, N panjang lah, panjang yang ni. This one, A plus B. Okay. So, this is the output of the modulator just now. And this one is what I told you just now. Increase, just add up. And then, we have EM cos omega M, cos omega CT plus EM sin omega M, sin omega T. And then you do trigonometry. Okay. You do trigonometry, cos A, cos B. And then you have cos sin A, sin B. So that's why you have this equation. Okay. So if you notice, this one is upper side band. This one is also upper side band, but they are different polarity. Okay. So plus minus, this one is become 0. So ended up, we have lower component, EM over 2 half. Okay. This is half, right? Plus by half. That's why it become 1 EM. Then, in this case, only lower side band is being sent. Okay. For the indirect method. So, what if we want the question, now question to you, what if we want to send upper side band? Okay, because this circuit is going to send lower side band for indirect method, lower side band or single side band, suppressed carrier. So, if we want to send upper side band, what we need to change? Okay, this is 1 plus N plus. Let's say we want to send upper side band, what we should be doing? Okay, so next is vertical side band. Is only a portion of the band being combined with this full portion of the other side band. So full portion of the upper side of the side band, let's say upper side band, with the some portion of the band that we filter out. Okay, so this is actually sending upper side band with some portion of lower side band. Okay, so for the generation is VST 2 cos omega CT, and you will get double sideband suppressed carrier, and then we'll go to filter. Okay, then we're going to filter up that we only we don't want this one. Okay, we only want this one. Okay, okay, so we finish on the part of transmitter. Okay, where we actually learn how to do modulation, where we learn about double sideband full carrier, double sideband suppressed carrier, double and then single sideband double sideband full carrier, single sideband suppressed carrier, single sideband suppressed carrier, vertical sideband. Okay, and then what else we learn? Five lah, 5 types. The other type lupa saya. Tadi ada 5 lah. And then from there also, from the transmitter side, you learn how to generate. Okay, which predominantly have 2 methods. For each of them, you have direct method and you have indirect method. Indirect method is more challenging. But then after that, you will learn later from now, from this slide. Okay, uh, demodulation. Okay, demodulation for double sideband suppressed carrier, a double sideband full carrier, and so on. The same as above. And then after that, you will learn how to do detection. Okay, detection or receiving. We're going to try to retrieve back the signals. Okay, we try to maintain the signal receive. Okay, for example, kalau saya nak hantar, saya ada buku, receiver cuba nak tengok saya ada buku lah, tapi mungkin tak nampak sangat, tapi cuba extract the message tu seperti apa yang transmitter hantar, kita cuba dapat yang sama lah. Okay. So the process of recovering the modulating signal or the original signal, okay, conducted at the receiver. So this is the what we call as a demodulation. Okay. Demodulation is performed by demodulation circuits. Okay. Sometimes we can use the word detector. Sometimes we can use receiver lah. Tak kisah. Tapi either way is demodulation and detector. Okay. At the receiver part. So this is your what we learned so far, and this is what we learned from now. Okay. So the simplest and most economic detector for AMC is envelope detector. Okay. The most simple and the most economic, senang and it's not complex. Envelope detector. However, this envelope detector is only for double sideband full carrier. Okay. So that's why double sideband full carrier still popular, even though carrier pun hantar kan, macam tak efficient carrier hantar power wastage and then masih hantar double sideband, even though sebenarnya uh, each of sideband sama je information dia, tetapi at the detection part ada kelebihan dia lah, sebab detection dia simple, the circuit is simple and circuit tu murah. Okay. So via envelope detector. Envelope detector cannot be used for DSB-SC and SSB-SC. Okay. There is one we'll see along the way. Okay. So AM DSB-FC double sideband full carrier demodulation. The circuit is envelope detector circuit, but also have another name, a rectifier detector circuit or diode detector circuit. Why? Because we have diode here. Okay. So the names is pretty much relative to what we have. So ada tiga nama, rectifier, diode detector, envelope detector lah. Okay. So make sure you tahulah bila kita cakap diode detector tu jangan you apa ni tak pernah belajar pula. Dia ada nama ke. Okay. So cost efficient, simple implementation, no need to generate local carrier LO. We don't need to do that. This one you will learn along the way later. Okay. The original signal is located at the envelope modulated signals. Okay. So in the double sideband full carrier, okay, the original signal is located at the envelope. Okay, the original signal. The original means the VMT. Okay, but how we do it later we'll see. Okay, so this is the envelope equation, EC plus EM, and this is your carrier. So this is the signals that you receive, VAM, amplitude modulation, going through here, and it passed through the point of one point, the first point, diodes. So if, as you learn from the circuit, the subject as what is it? Electronic devices, diode only allow current to flow in one direction. Okay. So because we have this one is positive, so masuk ke sini, bila dia lepas diode ni, kita akan dapat just portion positif lah. Negatif hilang. Maksudnya kita akan dapat, maybe it's already shown at the other slide. Okay, it's better this way. Okay, so this is the original signals. And then after pass through diode, we only take the positive portion. If our diode is reversed, okay, it means we only take the lower portion, the negative one. And then what? And then after that, it's going through this circuit, as we know as the low pass filter. What does it mean by low pass filter? We only allow low frequency to pass through and block or degrade the higher frequency component. So if you know, and if you as we learned just now, we have the carrier component inside here. Okay, this one carrier component inside our modulator signal. That's why after pass through, low pass filter, because it's high frequency component, it's being filtered out. That's why you no longer have this. Okay, you no longer have this because it has been filtered out by our low pass filter. So you only have this signal. Okay, and after that, it will go through DC blocker. DC blocker will remove the DC component exists in the signal. So let's say this one is DC blocker. Let's say maybe this one. Let's say this one is 5 volt. Okay, so the DC blocker will remove the value of the DC exists. Maybe there is actually the DC exists by 2.5. So after going to DC blocker, it will remove the DC component of 2.5 volt. So you're going to have uh 2.5 lah. 2.5. They say 2.5 is bring down by 2.5. The shape is not really accurate lah. Kejap tak cantik fokus. Dia kena bentuk macam okay. This one will be bring down. So let's say this is the original axis. So it bring down by, for example, 2.5. Let's say we try to use different colors so that you can relate. Okay. So this is the upper and this is the lower frequency. Okay. Lower value. Okay. Let's say this one is 0. Okay. 0, 0. And this one is okay, balik lah. Okay, so this one is 5. Okay, the original signal, let's say here. I mean this one after going to paid pass filter. Okay, and then DC component blocker will remove, not reduce, will remove the DC component exist. They say DC component exist here is maybe 2.5. So this one will bring over lower by 2.5. So now you have uh different value. Okay, let's say we reduce by 2.5. Okay, I try to use different color. Okay, okay. So now our signal is bring lower level. Okay, by DC blocker, maybe there is 2.5 VDC exists. So then it will be bring lower down. Okay, so no more DC component. So it is the same as the original component that you sent before is VMT. This is our message signal, the original. This is our message signal that is sent before. That is we have these signals plus with our carrier, okay, at the transmitter side. So this is the original signal VMT. So at receiver side, after having go through the detector circuits, we will have the signal same again. Okay, but maybe reduced in amplitude and so on, that is normal. Okay, so by having this envelope detector understanding, you will learn about the discharge rate because we having capacitors, okay, and inductor. So time constant is equals to RC. Okay, if RC is too large, the voltage drop is too slow, that cause diagonal clipping. Okay, this actually you learn from electronic device lah. The 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 charging rate, okay, that causing the time constant to be vary, and if it's too large, we have clipping. If too small, we have ripple. So if its RC is too large, the voltage drop is too slow je. Then we're going to have a diagonal clipping where part of the input voltage cannot be detected. Okay, clipping, diagonal clipping. If RC is too small, okay, the tau constant, the time constant is too small. This is time constant. Then we will have a lot of ripple sebab dia macam menjunam. Jatuh too small. So dia nampak bergigi-gigi. So instead, your VMT maybe it become bergigi-gigi lah. Terlalu banyak gigi dia. Okay, ripple. Kalau if RC is too large, then you akan nampak dia clipping lah. Okay, different Yang ni akan buat dia nampak gigi-gigi-gigi. Okay, ripple. So we have the words here ripple lah. And the desired message signal will be distorted. This is the RC of the capacitors. Okay, remember we have capacitors in our circuits. Okay. In order for us to have a good value, not too small of a time constant or not too large, so it must obey this equation. RC must not be greater than 1 over omega m. Sorry, RC must be equals to 1 over omega m, almost equals. Okay, so this one is, if you want to use modulation index, it must be less than this. So this one is in your appendix, if I'm not mistaken. Okay, okay, this one is just already shown just now. Okay, gigi-gigi nampak tak ni? Kalau you buang ni, you akan nampak dia macam ni. Okay, you imagine like this. If it's optimum, is almost like macam you punya VM macam cantik je macam ni. Dia pun lebih kurang lah. Okay, your VM. Okay. Simple mathematical analysis. Oi, kenapa besar ni? Okay. So assuming diode is like a switch, that is voltage VD. Okay. So, kejap sama tak dengan slide dekat PDF korang? Macam tak sama je? Tak sama kan? Ada silap ni. Can you check your slide? I think it's not the same. Salah ni. Yang ni ada tertukar. Kejap
Ya, doktor, lepas ada diode tu, circuit ada diode tu,
Ya.
slide seterusnya kalau doktor share tu 53 impact of RC value, yang tu lepas tu simple mathematic analysis.
Simple mathematics analysis tu salah kan equation ni kan? Macam ada lainnya.
Tengok doktor punya.
Saya putar yang saya PDF yang saya bagi you tu betul.
Oh.
Sebab yang saya ni kejap saya nak buka balik. I want to open my slide. Okay. My PDF slide lah. Kejap Sebab dia kadang-kadang our Google Scholar pula. Our Google slide dia tukar kita punya PowerPoint tu. Jadi dia jadi pelik. Okay, kejap nak tengok this one. So PDF tak tukar. Sepatutnya tak tukar boleh sini. Kan hilang ni kan? Perasan tak? This is the one that you receive kan? Okay? Dekat PowerPoint saya dia hilang. Dia jadi macam ni pula. Okay?
Lari
Satu
kot
saya
kata.
perasan. Ha?
Dia punya format terlari kot.
Ya.
Random ke.
Saya perasan. Satu saya terus ni. Okay. So, if you see this, okay, assuming that the diode is function like a switch, VD equals to EC plus VM cos T. K is the switching function of the diodes. Okay. Uh, Final exam untuk student is it final exam? Final exam student hari tu last semester dia dapat soalan macam ni lah, susah sikit lah. Ada diode switching function. Okay. Where KT is the mathematical expression for the diode switching function, VD is actually equals to EC plus VM. Okay. Overall here, this one, if you see overall here, all of them is actually uh, your DSBFC overall here, until here. And then multiply with K. So the K is the diode switching function given by this. Okay. You are not supposed to produce the diode switching function. Perhaps it's actually given to you. You just need to do the operation. Yang operation tu yang challenging lah. Okay. And then VD is V point B at here means after passing through diodes. So you're going to get 1 over pi EC plus VMT. Because this one is continuous, okay, until omega C, 3 omega C, 5 omega C, 7 omega C, and so on. That's why we replace with the words higher frequency terms, okay, kerana terlalu panjang lah. So 1 over pi EC plus VMT. And then it go to the low pass filter resonance frequency at FM. Okay, because it's a low pass filter, it remove all the higher frequency terms. That's why you don't have any more higher frequency terms. That's why you have at point C, after going to low pass filter, since this is your low pass filter, you will have 1 over pi EC plus VM with no high frequency term because has been removed. And then V point D, since capacitor C prevent direct current, okay, capacitor is actually is our is AC component, right? Okay, we don't have capacitor and inductor in DC. If we have it will act as either open circuit or short circuit. Okay, so by having C here, uh, it will behave as a DC blocker. It will remove all the direct currents and only maintaining the signal with frequency component. So at V point D, it will remove the EC. You can see, right? EC is the direct current. So remove this one and up, you only have 1 over pi times VMT because EC is being removed. Okay. So this one is the visualization of that. Okay. Of that explanation just now. Next is demodulation of AMDSBFC. Okay. Demodulation of AM double sideband full carrier. So you have a square law detector, AM double sideband full carrier, and then it will go to square law detector where the signal is timed by 2, no, by time 2 by square. So that's why you have XT here as your double sideband full carrier, okay, signals being squared, okay, and then because it's a cause and combination, so you just do what you used to do last time when you are at secondary school, right? So it's actually you just multiply them, you just duplicate them, then end up you're going to have this, okay? Just like last time in the past, you have x squared, 2 AB A plus B, A plus B lah. So you're going to have A square plus B square plus 2AB. So that's why you have two here. Okay. And then get rid of DC component. Lari lagi benda ni. Get rid of DC component is done by our capacitor. Okay. So we get rid of the DC component. Ya Allah, kenapa terbalik semua ni? So I have to use the slide again. Sebab dia menukar saya punya very bad. Tukar juga sini. Later I will maybe I will share to you again. Sebab tukar macam ni kesian sudah. So get rid of DC component. Harmonic frequency is actually the repetition of the frequency. Okay. DC component simple. DC component is component that didn't have value. So DC component, for example, 0.5 S square is a DC component. Okay. Message signal is the one in blue. Okay. After going to low pass filter and capacitor, output is desired message signal YT equals to AC MT. Okay. So this one is your message signals, VMT, is what you understand, with a multiplication of AC. Multiplication, no problem. What we want actually when we retrieve the signal, we want this the same shape, okay, and then the same characteristic. Okay. Different in amplitude, not a problem because it can be changed using amplifier or it can be brought down. Maybe depends on what we want to use, transformer ke apa, to reduce down. And then we have ASB, D double sideband suppressed carrier demodulation. Okay. Harap slide ni okay lah. Okay, double sideband suppressed carrier demodulation. Since envelope of the modulated signal is different from the modulating or message signal, one cannot use the envelope detector to demodulate. Okay, betul lah. Sebab envelope detector, like I told you, envelope detector is only for double sideband full carrier. Its demodulation can be performed using a synchronous detector or also known as coherent detector. So this one is for double sideband suppressed carrier. We use synchronous or we use coherent. Nama sama je. Nama bukan, benda sama, nama lain. Okay. A synchronous detector for double sideband suppressed carrier. Okay. So we will need to use a local oscillator. Okay. Local oscillator is a oscillator which is tuned, okay, which is tuned at the frequency similar with our carrier frequency. Okay, so this one is at the receiver side. We receive double sideband suppressed carrier. So we must inject cos omega. We must inject similar frequency. Means this tells us that we must have the information of carrier frequency in the first place. Kalau tak nanti kita tak tahu. Okay. Kalau tak nanti kita tak generate yang sama lah. Okay, and then after that, from there you will have XT, and then you will have low pass filter, and then you will have your own value. So multiplier, hilang juga kan ni? Kenapa terbalik macam ni? Nanti saya semak Pelik juga dia terbalik-terbalik ni. Okay, So a local oscillator to generate local carrier is required. The generated signal has to be synchronous. Macam saya cakap tadi lah, mesti sama. Okay. Dia tak boleh, this one carrier frekuensi 10 megahertz. Okay, carrier dia. Yang ni pula 10 kilohertz tak boleh. So dia kena sama supaya dia mix nanti, multiply, then you will get the process lah what you want. So XT is actually here is AM, DSB, cos omega CT because they are the same frequency, okay, as they should be. So cos omega C times cos omega C, you will get cos omega square omega C. M is the basis signal. So the sebab dia asyik berubah ni, M ni yang M yang your message tadi lah, yang apa, okay. So this is your M lah. Okay, output from the mixer. So this is the mixer. Okay, output from the mixer. MT cos omega t. Then we go for the trigonometry identity. So you learn from the cos square theta equals to half 1 plus cos 1 cos 2 theta. Okay. So using this concept, you masukkan this concept to this. Okay, this concept. So you will have for the cos omega ct, you will replace it with, you replace this one inside this one. Okay, you substitute. Okay. So that's why you have half mt 1 plus cos omega ct. In the end, when you expand, you have half m plus half m cos omega ct. Because it will be connected next to low pass filter. Here, after it's finished here, it go to low pass filter. Low pass filter will remove higher frequency components. So in here, if you see the higher frequency component is this 2 omega c. So that's why I remove by low pass filter. So you only have half m. So you will have half em cos omega m t. Okay. So what we can see from here is as well, our detection signal, the signal that we retrieve is actually smaller by half compared to the original, smaller by half. But no problem about this smaller, as long as the same shape, the same characteristic, okay? Because this is, if we want to compensate, we can just simply connect to amplifier with gain 2, okay? Because half times by 2, you get, half by 2, you get 1. So you get the similar signal again. Okay? So here, if you want to exactly, you just tambah lagi lah satu amplifier. Next is the impacts of the carrier frequency and phase error. Okay, impacts of the carrier frequency and phase error. When there is phase frequency difference between the locally generated carrier frequency and input signal DSPSC. Okay, so this one is if we have error. So here is error in terms of carrier frequency and error in terms of the phase error. So let's say our local oscillator, we try to generate cos omega ct, right? We try, okay? But however, there is possibility that there is error happen at our local carrier, either in terms of the frequency or the phase, okay? So if we extend with the error or without error, let's say we have omega c plus changes of omega and t and plus with phi. Okay, if phi is not equals to 0, means non-zero, so there is possibility we'll have phase error. Similarly, if there is delta omega is not 0, having some value, so you may have carrier frequency errors. Okay, or if you have both of them is not 0, then you have error mix from both of them. Okay, So this is the phase error if it's happen. This one is frequency because this one is frequency, right? 2 pi f. This one is angle. Okay, phase. So if this is happen, this lead to distortion during the modulation process of double sideband suppressed carrier because it's supposed to be only this. Okay, but system may be not ideal. It can generate errors. Okay, let's say we have problem with the phase error. Okay, where the error is not zero, but maybe the error coming from carrier frequency is zero, but the phase is not zero. So we have this effect. So by trigonometry identity, so our cos A now is actually become omega ct A, but our B angle is with phase error omega ct plus phi. It's different. It's supposed to be identical. So because of we having them as difference, so we're going to have the result from the trigonometry identity operation. We're going to have cos pi and cos 2 omega ct plus phi plus phi. Okay, by letting xt into the low pass filter, okay, because it will go through low pass filter, right? When it go through the low pass filter, we will still remove the high frequency component. However, because the error is existing in the phase here, so the signal that left over that being filtered out, not and not having higher frequency, it still have this phase error with cos phi. So implication of the carrier phase error, okay, phase error, not carrier frequency, phase error. If the phase is zero, like I told you just now, if the phase is zero, no error happen means we get the exact signal. It's just as reduced in terms of the magnitude. However, if our phi is pi over 2, we potentially lost our signal. Why it is equal to 0? Tak ada. So this how important or how effect the phase error can contribute to our signals. Okay, so doesn't necessarily phi is 0 or phi equals to pi over 2. When you have error, we can have other phi, for example, 3 pi over 2, okay, and 3 pi over 4, and so on. Okay, this one is just to show you the effect of the base if we have it 0, and the worst maybe the worst can happen is we lost the signal. Okay, then the next is Costa loop PLN. This one is phase lock loop. The long name is, okay, to ensure that L of S is fixed with reference to the characteristic which result in maximum mass signal. So what Costa loop going to do is that kalau ada shift dalam kita punya phase, dia akan cuba kembalikan kepada phase yang asal lah, atau dia akan cuba adjust supaya phase itu bersamaan dengan atau bersamaan atau merujuk kepada carrier frekuensi. Jadi dia akan cuba samakan balik. So bila dia samakan, dia akan dia akan dapat menghasilkan maximum signal. Okay? Dengan ada PLL tu lah. The loop has a voltage control oscillator that will be locked to the carrier frequency of the signal with only small phase error. So voltage control oscillator, what does it mean? We control by this term, VCO. We control the frequency, which is oscillator, by the oscillator by having the voltage being manipulated. So that's why the name voltage control oscillator. We control the frequency by varying the voltage. Okay, this one also pelik juga. Okay, so double sideband, single sideband suppressed carrier. Now single sideband, just now is double sideband. Okay, just now is double sideband suppressed carrier. Now single sideband. Okay, single sideband suppressed carrier demodulation. You have almost similar, but the receive part is actually single sideband suppressed carrier lah. Okay, so error implication. Okay. Kejap Memang ditukar habis, pelik betul apa saya punya Google Slide ni. Bila dia download PowerPoint dia jadi pelik pula. Okay. Okay, this one. Okay. Bila kita tahu tu slide kita, kita tahulah dia tukar pun kita tahu dah macam lain. Okay. Okay, so this is single sideband suppressed carrier demodulation. So we have this is similar, but we just change the input lah. Input to our receiver, not input to our transmitter, input to our receiver. So upper sideband, let's say we receive single sideband suppressed carrier upper sideband. So with amplitude of 1, we receive this. And then what we have V naught. V naught is VSSBSC dot VC. So this is V naught is here. Sorry. V naught V naught is here. Okay, V naught is here. V naught is here. This one is VLPF lah. Okay, this one is VLPF. A bit error, sorry. V naught is here. VLPF is here. Okay, so V naught, which is here, is VSBSC dot VC. So cos omega C plus omega M. So we only receive upper sideband that time because single sideband suppressed carrier. Then dot multiply with our cos omega C. So we end up having this equation with a mix of message and also a higher frequency component. After that, we want to filter out the carrier because we don't want carrier at our receiver. Kita nak buang, kita nak ambil kita punya message je. That's why in the end we implement low pass filter. So low pass filter we remove omega C. So that's why we have after LPF we have VLPF half equals to cos omega MT. So we remove this once semua ni. So kita tinggal yang ni je. Yang ni darab half. Okay. So the same implication of phase errors as what you learn from the double sideband suppressed carrier lah. Okay, the same concept. The next is VSB, vertical sideband detector, similar to DSP-SC and SSB-SC detector, but the input signal is VSB signals. So similar. So this will be VSB. Okay, similar to the both concept above lah. Sekejap tengok. Okay. Okay, okay. 1, 2, 3, 4, 5. Oh, boleh habis. Okay. Super heterodyne receiver. Super heterodyne receiver. Used in the commercial AM, FM radio lah. Contoh Zayan FM, Era FM and so on lah. So RF signals, radio frequency signal, 540 until 1600 kilohertz is received, is translated to an intermediate frequency, 455. The word translated is actually shifted lah. Okay, the operation here. Okay, you see here, shifted. Okay, for the purpose of amplification, filtering, and demodulation. Okay, the device that perform the modulated signal frequency translation is known as frequency mixer. The operation is called frequency mixing or conversion or heterodyne. Ada banyak nama lah. The translation tu nama lain dia mixer, mixing, conversion, heterodyne. Okay. Tiba-tiba yang mana mak-mak tu ingatlah mixer dah beli tak mixer atau kuih-kuih biskut-biskut okay, atau belum buat kuih dia. Okay. So VLO, FLO is local oscillator. FRF is this 540 until 1600 any frequency. For example, maybe 800 boleh 800 and plus minus 455 kilohertz. Okay. IF is fixed value 455. The RF is the range, depends on which one. Okay. And then super heterodyne receiver, this is the system. Okay, at the receiver side. So RF signal amplitude modulation in the range of 540 until 1600 kilohertz. You have antenna receive that, and then you will have RF tuner. RF tuner is macam bila you dengar radio tu, you perasan tak you tune kepada frekuensi yang you nak. Yang tu lah. Okay, RF tune. Tune to the frequency that you want because you have a lot of frequency coming in. Era FM, Hot FM, Zayan, National FM, macam-macam lah. Masuk, dan you tune kepada yang you nak. And after that, you going to amplify that signal because the signal is weak after coming through from distances and whatever, disturbed by noise. So that's why we amplify the weak signals. Okay, what happened after that? This is the signal that you have. Okay, A plus M cos omega ct, the amplitude modulation. It's going to be mixed. It's going to be mixed with our local oscillator FLO equals to FC plus minus IF. It's going to be mixed here, and then you will going to go through to the IF filter. IF filter is we going to remove the intermediate frequency. Okay, and then you're going to have FIF here, FLO plus minus FC, and then IF amplifier, intermediate frequency amplifier, and then you only then you go to the envelope detector that you understand just now, where we have diode, we have low pass filter, we have DC blocker. This is small part of them. The rest is super heterodyne receiver with envelope detector being one of the elements. Okay. Okay. Sikit dah habis. How frequency conversion is done. Okay. Okay. Before I sambung, takut I lupa 2.11 ni sampai ke bawah tidak ditanya dalam soalan final exam. Jadi jangan risau. 2.11 nanti bawah tidak ditanya, cukup untuk good to know. Jadi saya tidak akan present lah, saya tak akan ajar sebab nak bantu you, kalau tak nanti berat you. Kita dah nak habis ni, pas tengah. Okay, where was I? Okay, again repeat 2.11 and above will not be covered, will not be asked in final exam or test. Okay, just a good to know. Okay, solution, A plus MT cos omega C times 2 cos omega L t. This one is XT. XT is this one. Mixer with this. This is your XT. Okay. This one mix with this one. This is where you get your XT. Okay. So 2 cos 2 omega L naught t. So we purposely put here 2. Okay, because later on when you times with half, because cos omega M, cos A, cos B, you will have half, right? By putting 2 here, you will make them become 1. Okay, this one is just for easy understanding lah. It's not why suddenly have 2. Okay, 2 is to counter to make up the equation easier, so that resultant of cos A cos B that result in half will be times with 2 becoming 1. Okay, So AM cos omega C naught, omega M naught T, and cos omega C plus omega M naught T. So you no longer have the half, otherwise you will have half. So where omega L naught is omega C plus omega F or omega C minus omega F. That's why you have plus minus here. Okay. If we select omega C minus omega F, if we want this, okay. So our ST will have A plus MT omega F naught. You just insert, okay, omega C minus omega F, insert. This insert. Wait for a while. Maybe I use. Okay. So if you choose this one, you just plug in this one inside because omega F naught. So you have omega C minus omega F naught. Okay. So omega C minus omega C 0, right? But minus minus you have plus. That's why you have plus here. And the same goes to here. You need to plug in. Then you have this. Similarly, operation for this one. Okay, you plug in. Then you end up having this and this. Okay. And then after that, band pass filter tuned to omega IF will pass A plus M cos omega IF. So if we go to the band pass filter where, where we only want the lower frequency component. Okay. Mm, so higher frequency component omega C omega C minus omega F if we choose this WLO, or if you choose this omega N naught omega C plus omega F. So if we go through the filter, the high frequency component will be removed. Okay. So filter will remove the high frequency component. If we go to band pass filter is tuned to F, we pass only this, but the high frequency component will remove because this one is high, right, to omega C. So that's why you only left either this one or this one. Okay, depending on which WL node that you choose. Okay. Okay, so this is how to show you the concept of filtering. Okay, pretty much as what I explained already. It's shown in graphical how they done it. So this is your bandpass filter lah, bandpass filter. If it's choosing the choosing we depend on the what we choose lah, whether omega L, omega C minus omega F or omega C plus omega F. Okay. The super heterodyne advantage is overcome weakness in some component that could not operate at high frequency because not everything can operate at high frequency because we have limitation of the circuit. Okay, some circuit, if we want it to operate at high frequency, the device become more expensive. Okay, okay, azan ni kejap 3 minit sekejap. Kita dah nak habis jangan risau. Saya aim 4.5 ya. Sikit lagi. So kita continue, almost finished. So the advantage of having super heterodyne is that we try to overcome some components not able to operate at high frequency, and also component we able to operate at high frequency is usually more expensive, and the circuit that operate at higher frequency may be also more complicated. So that's why we use the concept of super heterodyne, where they are bring to the same fixed frequency, IF we call them, is at 455. Okay. For the AM radio, amplitude modulation radio, the IF is 0.45. So this one is error. This one is 455. Okay, not 0.55, 455. Okay. Please correct your slide. This one is 455. Uh, so the IF bandwidth 10 kilohertz. FM radio, the IF frequency is 10.7 megahertz. A lot of the radio has been using FM radio. You don't really know AM, right? You just listen, for example, Hot FM, Era FM, semua ni FM lah. This is where the frequency modulation names comes from. That maybe you familiar with your real life lah. You can relate lah. Okay, this is the FM radio lah. So SNR is not being asked in the final exam and the test, so I won't go through them. So again, I will share again the attendance. You can scan your attendance, and then you can fill in your attendance, and you may leave after that. Okay. Uh,